Today, we're talking about modern-day alchemy. I mean, really. We're going to look at how scientists are taking industrial waste, stuff we'd normally just throw away, and using it to remake the very ground we stand on. Think about it. We build our entire world on soil. Our homes, the roads we drive on, our cities, everything. But what happens when that foundation, the literal ground beneath us, is weak? Or even worse, what if it's poisoned with chemicals that can get into our water? And this isn't some rare, isolated problem. No, it's a huge challenge that engineers and city planners are grappling with all over the world. But here's the twist. The solution isn't some fancy, expensive new technology. It's actually hiding in plain sight, in the junk piles of our own industries. Okay, so before we get to the solution, we really need to understand the problem. There are two major threats that are making the ground right under our feet pretty unreliable. So you've got two big enemies. First, there's a physical one, especially in cold places. You know, the freeze-thaw cycle. Water in the soil freezes, expands, and it literally shoves the soil particles apart. Then when it thaws, the soil is just weaker. We're talking a massive 38% loss in strength. And then there's the chemical threat. Things like leaky underground fuel tanks can spill really nasty stuff into the ground. A big one is MTEB, a fuel additive that travels super fast through soil and groundwater, and it's a serious health risk. So our soil can be physically weak and chemically dangerous. Where does the fix come from? Well, it turns out the solution comes from some pretty unexpected heroes found in industrial waste. Right, instead of trying to manufacture some brand new material, which is almost always expensive and takes a ton of energy, scientists started looking at what we've already got plenty of: industrial waste. It is a genius bit of upcycling, but on a massive, almost geological scale. So let's meet our unlikely team of heroes. First up, from iron and steel production, you get this glassy stuff called GGBS. Then from cement factories, there's CKD, which is basically a super fine dust that would otherwise just be landfilled. And finally, you have kaolin, which is a really common, soft type of clay. On their own, they're just leftovers. But when you put them together, oh, that's when the magic happens. So how do these humble materials become a kind of super soil? Well, the secret is in a really clever bit of chemistry that essentially creates a superglue for the Earth itself. The main technique is called stabilization and solidification, or just SS for short, and it has two jobs. First, make the soil stronger. Second, lock up any dangerous contaminants inside a solid block. You're basically turning loose, polluted dirt into a single, stable, and safe chunk of man-made rock. And the recipe is basically a four-step process. First, you use an alkaline solution to wake up the waste materials. That's the activation. Then, this activated binder reacts with water and it starts forming these really powerful cement-like gels. Next, those gels all link up with each other, creating this incredible 3D network. That's our super glue that holds all the soil particles together. And finally, as this new matrix hardens, it physically traps the contaminants, locking them away so they just can't get out. Okay, that recipe sounds amazing in theory, right? But does it actually hold up in the real world? To find out, scientists put this new super soil through an absolutely brutal series of tests. To really prove this thing works, the stabilized soil had to run a whole scientific gauntlet. I mean, they threw everything at it. They used strength tests to see how much pressure it could take before it cracked. They put it through freeze-thaw cycles over and over to mimic harsh winters. They ran leaching tests to make absolutely sure no poison could escape. They even looked at it under a super powerful microscope to actually see the new superglue structure that had formed. And the results from all this intense testing, they were nothing short of spectacular. I mean, the stabilized soil wasn't just a little bit better, it was a complete game changer. Get this, the original untreated clay soil, it could handle about 146 kilopascals of pressure. But after mixing in just a tiny 1% binder, its strength rocketed up to over 1,300 kilopascals. That is almost a 10-fold increase in strength from just a little bit of activated industrial waste. Incredible. So it's stronger, but what about the poison? Well, the results there were just as mind-blowing. The SS process was so good at locking away the MTBE contaminant that it cut the amount that could leak out by over 91%. The poison was officially locked down. And what about durability in the cold? Remember how that natural soil loses 38% of its strength after freezing? Well, the stabilized soil, it didn't just survive the same treatment, it ended up being over 30 times stronger than the original unfrozen soil. It doesn't just resist the damage, it actually seems to thrive on it. And hey, don't just take my word for it. The scientists' own conclusion put it pretty plainly. The method works. This isn't just a cool idea anymore. It's a proven, effective way to both strengthen soil and clean it up at the same time. So what does all this mean? This research is so much bigger than just a lab experiment. It really points the way to a smarter and, honestly, a much more sustainable way of building our world. I mean, why does this matter? Well, for one, it turns something we think of as waste into a valuable resource. That means less stuff in landfills. This whole process also has a way smaller carbon footprint than making traditional cement. And, maybe most importantly, it lets us build stronger, safer roads, buildings, and foundations for less money. It's a win for the economy, a win for the environment, and a huge win for engineering. And that really just leaves us with one big question to chew on. We live in a world that is producing just mountains of waste. And at the exact same time, we desperately need to build a more resilient future. What this research shows us is that maybe, just maybe, the answer to one of those problems is sitting right there inside the other. Perhaps the ground beneath our feet is just waiting to be remade with the very same stuff we've been trying so hard to get rid of.